Hello, welcome back. Dr. Doyle here. I'm going to talk to you a little bit about residence time. I'm going to try and not block my face today in this video. Let's see how this goes. Residence time as it pertains to water resource engineering. Residence time, when we talk about residence time, we're really asking how long a parcel of water stays in a control volume. CV, control volume. And we care about this for lots of different reasons. And I'm going to mention another class quite often when we talk about water resources, and that's environmental engineering. When we talk about these two courses together, it can be really powerful. Residence time is really important in the context of water resources with environmental engineering because it gives us a clue about how long of a time we have for particular reactions to occur. In the context of water resources, it just gives us sort of like an age of how long water stays in a particular control volume, and that can be really powerful for us to know. We often talk about the age of water molecules in the ice caps or in the ground, and we'll do some calculations to show that. But today's example that I'm going to do is an example of the residence time of water in an average human body. Okay, so example, how long? My daughters have been playing with these pens, and the blue one is not great. I need a new blue one. Does water stay in an average human body, an adult? We're going to do this using the calculation. I forgot to write it over here. So the residence time, T subset res, is equal to the volume divided by the sum of the inflows. Okay? And that's feeling, what's the wrong color? There we go. And if you look at the units of this, we have volume, so cubic feet, divided by cubic feet per second, which leaves us with second or time. Okay, so that's how we get to a time. This is a simplification. There's other ways, more complicated ways to calculate the residence time, but this is what we're going to go with in this class. So, in order to know how long water stays in the average human body, we need to know a little bit about an average human body. So an average adult mass human body is about 70 kilograms. 60% of that is water, which means that that is about 42 kilograms of water. Okay. And we know water density is approximately 1 kilogram per liter. Because the density, I've mentioned this previously, it does change slightly with temperature, but it's not going to be enough to change our approximation here for how long water stays in the average human body. So this means that we have approximately 42 liters of water at any given time in the average adult human body. Okay, so we have our volume, we have our top. Now we need to think about the inflows. And so I'm going to look at the sum of the inflows in the average human body. This is really all the ways that we take in water. Now you'll notice that this doesn't include outflows, right? And again, as I said, this is a simplification. More complicated calculations do take into account the outflows, but we're going to only do the inflows. So the ways that I take in water, and most adult humans, are from two sources: food and liquid beverage, right? So as an approximation, let's just say that the sum of the water from our food, all of our food together is 1.5 liters per day, and the same for our liquids. This would give us 3 liters per day of inflow. And so this means that the residence time of an adult human is 42 liters divided by 3 liters per day, which is 14 days. So what does that mean? This means that on average, whatever you're drinking today or eating today, the water in the food that you're eating today is going to take on average 14 days to be expelled from your body. And of course our outflows, we have urination, but also sweat, tears, breathing, you put out some water. So on average, each molecule is 14 days. Some are going to be longer than that, depending on the pathway that each molecule takes, and some will be shorter. Some might be excreted within 24 hours. This is just an average. So you can see how you can increase or decrease this residence time. If you drink more water, if this number goes up, then you're going to have a faster residence time. So you'll decrease the time of water, the average time that the water is in your body. And if you drink or consume less water, you will increase this residence time. So we'll do some more examples together in class, looking not at human bodies, but instead at control volumes of the hydrologic cycle.